Hi, I'm Sergey Melnikov, and I would like to introduce you Geoffrey De Smet, and we will talk about planning, scheduling, and all this stuff. So, Geoffrey, just small first question. As far as I know, maybe I'm wrong. All these tasks are already solved. All algorithms are already invented, and it could be write down quite fast. I think I'm wrong. Could you?
Well, well, if you're dealing with scheduling and planning problems, what you can always do is brute force. You can try to actually try every combination out there for your plan and just look what's the best one. The only problem with that is it completely doesn't scale. It goes from seconds when you have a small data set to like for example assigning 10 or 20 items into a plan to years when you do 21 items, and then of course when you want to do hundreds of items, it can take literally billions of years, or even 10 to the power 80 years for just one to solve one problem with all of the CPU power on this planet today. So that algorithm brute force clearly doesn't work, and there's much better algorithms, but even many of those still run into scaling issues. And so one thing we do in our solver is we have all of these algorithms, including brute force, which you can try out, and then it tells you which is the best one, and then it shows you how they scale. And but we have a standard one, and that's the one that works very well in all cases, basically.
Actually, quite interesting. And how popular this task is? I mean, what is the value of solving this task better than previous? What is the value for maybe planet, us, and all this stuff?
Yeah, so planning problems are everywhere, right? And so today we'll be talking about maintenance scheduling. There's many others, like for example, vehicle routing, where you want to assign visits to a vehicle and decide which vehicle goes to which visit and in which order they go to these visits. And that particular one typically saves 25% driving time if you use a better algorithm, if you use a better solver to solve that than traditional algorithms or human planners who do this manually, or the old-fashioned way. And when you save 25% driving time, it really makes a big difference financially. It can actually, and we've seen cases where it saves hundreds of millions of dollars per year, and also ecologically, where it saves tens of millions of kilograms of CO2 emissions. So it's a win-win situation for everybody. It sounds weird, especially when you look at it as a human. At these plans, they look quite optimal already, and then when you use a real constraint solver, like for example OptaPlanner on it, what you will see is that there's this huge gap, and it's hard to imagine, but it is. We see this all the time, so it's quite interesting to see.
Great. I think I'm already looking eagerly to just understand how planning could help me. So maybe we could start, Geoffrey.
Yes, that's good. Let's get started. So I'm Geoffrey De Smet. I started 15 years ago a small open source project, nothing serious, but over the years it got very, very serious. It's known as OptaPlanner, and these days it's used all across the world for all kinds of planning problems. And one particular planning problem we're going to talk about today is maintenance scheduling, more specifically road maintenance scheduling. So I presume many of you might have already driven on the road and run into road maintenance, right? And they had to take a detour. And when you take the detour, what happens a few streets further, you run into another road maintenance, and you start wondering, why do they schedule two road maintenance in the same area at the same time? Can they not make better plans? How hard can it be, right? And I'll show you that it's actually quite hard and how we can avoid those situations today. And I'm going to do that using OptaPlanner on the Quarkus platform, and I'll show you the code how to do that. We're actually going to write this application, right? So this is our road maintenance scheduling application, and I'll live code the AI part of this, the planning optimization part of this for you during the rest of this talk. So what we're basically going to do is we're going to click the solve button, and it will give us a schedule like this, where we see, okay, Alpha Crew has to do maintenance on Uptown Highway on the 3rd of November, and so forth. So let's take a closer look at this problem. What is this problem? Why is it so difficult, right? Well, you have a number of jobs, like we need to do maintenance on Uptown Street, Uptown Bridge, Forest Road, Airport Tunnel, right? And each of these jobs takes a number of working days. Like Uptown Street takes 3 working days. And each of these jobs has a ready and a due date. So what is the ready date? The ready date means the job cannot start before that time, right? It cannot start before that date. For whatever reason, we don't want to do Uptown Street maintenance if we want to do it twice a year. We don't want to do it once in January, once in February. That's too close together. So we actually have a ready date 6 months after we've done the first time we did maintenance on that street. So again, the ready date is we cannot start before that date. It's not the date we actually start to work on. It's a hard limit, right? The next thing is the due date. That means that work has to be done before that particular date. It has to end before that particular date. In this case, that's the 5th of November, right? And then we need to take these jobs and put them in our schedule. And you can see here we have 2 crews, the A crew and the B crew. And we need to decide which crew gets which of these jobs, right? And we also need to decide when they get these jobs. When does the job start? And of course, when it ends, but that's actually depending on when it starts, of course, because you know how many working days it takes. So we could, for example, assign the green job here, the Uptown Street job, to let's say the 1st of November to start then on crew A, and then it would end the 3rd of November. But it could also start the 2nd of November, that would still be fine, then it would end the 4th of November. But we cannot assign it to the 3rd of November. Why not? Because then it will end just before the 6th of November, and it needs to end before the 5th of November, right? Because that's the due date. So you can see this here at the bottom too. This is basically the ready date, the due date, and this is the length in number of working days. And we need to decide for each of these, when we will put them for these two jobs, for these 2 crews. And there's an important thing, of course, right? One crew can only do 1 job per day. Right. And of course, once you start a job, you need to finish it. You can't intermix jobs within 1 crew either. What do we do? Think about this. If I give you this problem on paper, which job would you assign where? So would you start with, let's say, crew A starts with the green job and crew B starts with the yellow job? Would you be able to get a feasible schedule out of that? And I'll tell you a secret, you won't. Look at the blue job. You won't have time to actually finish that blue job in time if you start crew A with the green job and crew B with the yellow job, right? So we need a better solution than that. So let's give that to OptaPlanner, right? And then we give this problem to OptaPlanner, and then OptaPlanner tells us the solution. And here's the solution. You start crew A with the green job on the Uptown Street on the 1st of November, and crew B actually starts with doing nothing on the first day. That sounds suboptimal, but it is optimal. Why? Because if we would assign the yellow one, then that would end the end date would be between the 3rd and the 4th of November. So the end date is exclusive, so it would end on the 4th of November. And then we only have 2 more days to do the blue job, but the blue job takes 3 days. So that's why we need to do the blue job before the yellow job. The yellow job, the due date is quite long, so we can actually postpone that. So that's exactly what we're doing here. And you can see that we also take into account weekend days. So for example, the yellow job takes 3 days, but because it crosses a weekend, the days during the weekend don't count because they don't work during these days. So it takes 1 day before the weekend and 2 days after the weekend. And so this is what we're going to do. We're going to give OptaPlanner, we're going to take a data set, and we're going to give it to OptaPlanner using some our constraints, which we'll add, and we'll actually get a good solution, a feasible, near optimal or optimal solution. So this is not the only problem that OptaPlanner can solve for you, right? It can do equipment scheduling, like assigning hospital beds to patients or CAT scanners to patients, and increase the utilization of those items. It can do job shop scheduling, where we want to optimize assembly lines when we're building cars or furniture or anything like that. And when you can do combinations of, if you do multiple red cars in a row, can actually get the throughput of the assembly lines go faster, right? You can reduce the make spans of your jobs, again, increase efficiency of your factories. Vehicle routing, which Sergey and I talked about, right? This is about telling for each vehicle in which order they will visit which locations across the country. And when you do this, again, against traditional algorithms, we typically reduce 25% driving time. It depends from case to case, of course, but the gain on this against traditional algorithms or human planning is actually quite large. It's an easy investment to make if you have enough vehicles. The return on investment is very high. And then, of course, we have bin packing in the cloud, where we want to optimize our cloud to reduce our cloud's footprint, and employee rostering. In employee rostering, we need to assign nurses or guards or anybody else who doesn't work from 9 to 5, but actually works in multiple shifts, like a morning and a day shift, potentially even night shifts, to assign those shifts to persons with particular skills and so forth. And then in that case, we want to make sure that when one of these people says, okay, one of these nurses says, I want to be free on Monday, that we can hopefully give her a free day on that day, such that the nurses are happier, the service quality improves because the employees are better rested because they get enough sleep between two shifts and so forth, right? But today we're going to talk about about maintenance scheduling. So let me introduce you to the domain again. So if you remember, we had jobs up down which we have here on the side, and we have crews, the crew A and B, and then we have a number of dates to pick from to assign these jobs to one of those dates and one of those crews, right? So let's take a look at how that looks in a class diagram, which we'll show in code in a few minutes, right? So we have a crew, and that is a class which has one field, name, and which is a string to represent that crew. Now, in a more advanced, elaborate example, what you would do implementation, what you would do is you would probably have a skill or a set of skills here, or affinities to certain types of jobs, and we can just add it all in that crew, and then we can write constraints to actually take those things into account too. But for today's, I'm going to keep it simple. I'm just going to have the crew have a name, right? And then we have a job, right? And in this job, we have a number of fields, right? Like we have, again, the name. In this case, that was Uptown Bridge or Downtown Tunnel and so forth, right? And we have a ready date and a due date, like I've explained earlier. The ready date is it needs to start not before that date. The due date, it should not end after that date. And then there's a duration in days. That's how many working days does it take to actually do this job. And then we have a mutually exclusive tag set. I didn't really talk about that much yet, but that's basically for each job, we can assign a set of tags. And when two jobs have the same tag, they should not be happening at the same time. So for example, when we have two jobs in the downtown area, then we want to make sure that those don't happen at the same time. So we'll give them both the tag downtown, and then we'll add a constraint to make sure that they do not happen at the same time. But this is not just for the area. You can also use this, for example, we don't want to impact the subway network or the rail network too much. So if we have maintenance that actually impacts the subway stations or things like that, what we'll do is we can also add a subway tag in there, and I'll actually do that in the demo code. And then this job, we have 3 more fields, but these are not input. These are actually output, and that's which crew is assigned to that job. This is the thing which we need to find out. It starts as NULL, but after solving, we need to find out. We need to say for each of the jobs, which crew will do that job. And so this is a many-to-one relationship. Multiple jobs can be assigned to the same crew, just not at the same time. Of course, every job has exactly one crew to do it. And then there's also the start date, which we'll also need to assign. And of course, the end date, which can be calculated from the start date by adding the duration in days and taking into account for weekends, which I'll also show in a few minutes. So how do you get started? What if you would write this application from scratch? Now, I don't have the time in this presentation to write it entirely from scratch. I've only implemented, I will start from an implementation that has a CRUD implementation and some demo data, but no AI whatsoever. And that's the part that we'll actually add during live coding. But let's say you would start this from scratch. Now, what you can do is you can go to code.quarkus.io. And again, I'll implement everything on the Quarkus platform today. and I'll use Maven and I'll use Java. But you could do this with Spring 2, which also has in which we also have support for OptaPlanner. You could do this with Quarkus and Gradle, for example, if you don't like Maven, or you could do this with Quarkus and Kotlin if you don't like Java and you prefer Kotlin. It's all possible, right? But today I'll stick to Quarkus, Maven, and Java. So what you do here is, okay, we give our project a name, right? Like maintenance scheduling, maintenance scheduling, and we add a number of things that we'll need. So what do we need? Let's take a look what we will need. So we're going to use Quarkus as the platform. We're going to need a REST service, right? We're going to need we're going to send everything to JSON to the client, which is a JavaScript, a simple JavaScript code. And then we're going to go to the database using Hibernate JPA, right? So let's do that. So let's get Hibernate in here. Hibernate. We pick Hibernate with Panache. What is Panache? It's basically it's very much like Spring Data, where you can a bunch of CRUD methods to store your Hibernate objects easier into the database and so forth. We're going to use JSON, right? Let's use Jackson over here. Rest easy Jackson. Jackson. We're going to use, of course, OptaPlanner, right? This is the AI constraint solver. We're going to add OptaPlanner Jackson. That's again some integration with the JSON code for when we want to send certain things back to the client. And we're going to add the H2 database too, right? And so then we're going to generate our application. But like I've said, I've already have this locally here. So let me just show you that. Here we go. So I've already prepared a simple CRUD application that does this. So what do we have in here? I gave it a name, like maintenance scheduling, as you can see. I'm using Java 11, and if you scroll down, I'm using Quarkus 2.3 here, you can see. 2.4 is actually just out. And you can see we're using the OptaPlanner Quarkus annotation extension. We're using the Jackson extension to send it through JSON. We're using Hibernate Panache to go to the database, like I've shown earlier. We're using H2 as the database and in-memory database, and we're using the Jackson REST easy stuff to actually expose our methods as REST. So we can basically, so we have this architecture, right? So let's take a look at how that looks already, how that works already, right? So we can see here at the local host, when it refreshes, there's nothing running here. And when what I'm going to do now is I'm going to start Maven Quarkus Dev. And this is for me the most brilliant thing that Quarkus did and does is Quarkus Dev. So everybody's excited about native compilation with Quarkus, and we can do that too, and it's all fun, and it's all fast startup and great for serverless. But for me, the real change is Quarkus Dev Mode, and I'm going to show you in a few minutes why this is so why this is a big difference from the past. So what I'm going to do is I'm going to run Quarkus Dev. So here we go. This is the terminal at the bottom, as you can see. Let me clear that. So I'm going to run Maven Quarkus Dev, and and when I make changes in the code, Quarkus will immediately show me those in my browser, and I'm not going to restart this anymore for the rest of this presentation. If all goes well, of course, you never know what the demo gods will do. But you will see when I make changes, they will immediately be shown in the UI. You saw a warning there too. The warning was actually that even though I have OptaPlanner in my dependencies, there is no OptaPlanner code in here. So when I actually do find me OptaPlanner code, it actually finds. It does find an import. It is unused. Look, there is no OptaPlanner code in here. Just to show again, there is some, except of course in the UI, there's an OptaPlanner logo in there, and that's what it finds. So there's no OptaPlanner code in here. And let me show you what I have so far. Right. So let me refresh here on localhost 8080. This is our CRUD application, right? So we have our jobs, Uptown Avenue, Downtown Bridge, Downtown Street, and so forth. This one takes 6 working days, has a ready date of 4th of November, has a due date of 2nd of November, and you can see we have quite a number of jobs, and we need to assign all of these jobs into our schedule in a 5-week schedule, no, an 8-week schedule, sorry. And just to visualize it a bit better, here is the visualization per job. So this is the Uptown Avenue job, 6 working days. The ready date is the 4th of November. The due date is the 22nd of November. So this job needs to be scheduled in this green period. And you can see that, and it takes 6 working days to get an idea of where we can put it. Of course, weekend days don't count as working days. So if we would actually schedule it to the 4th, it would actually be 2 days longer because we cannot work the 6th and the 7th of November because it's weekend. You can see we have a whole bunch of these jobs. They differ in number of working days. They differ when their due dates is and when their start dates is. And we need to make sure we assign them to the right time and of course also to the right crew. So we have 3 crews here, the alpha crew, the beta crew, and the gamma crew. And so we'll need to assign those to those. So let's take a look at the code behind this. Let's start with the domain, right? So just a second, here we go. Like I've shown earlier, there was a crew class, right? And if you remember from the domain model, and in this is the crew class where we have the name of the crew, and we also have a database ID because we will store this in the database. Beyond this, we have a bunch of generated getters. We have a toString and a bunch of constructors. So all of this isn't really important. This is the only important part of this, right? We have the class crew. It goes into the database. That's the entity annotation. For those of you familiar with Hibernate and JPA, this basically says there is a table in the database crew, right? And when I save this crew instance to the database, this is how you need to map it. It has an ID. So here we tell Hibernate that's the ID. Here we tell JPA this is the ID of that class, and we want that ID to be generated by the database. We don't want to worry about it ourselves, and you see I've chosen a long here in this particular case. The name is just a string, will also just go into the database, right? So that's the crew class. Then there's also the job class. So here we have the job is also an entity. That means it's also in the database, right? It also has an ID. That means that, and which is also generated by the database. Then it has that name, which I talked about earlier, like Uptown Tunnel or Downtown Tunnel or Downtown Bridge or something, the name of the job that needs maintenance. The ready date and the due date. Now, the ready date is inclusive and the due date is exclusive. Like most ranges in Java are, the start is inclusive, the end is exclusive. So we follow that pattern here too, and that makes the math a little bit easier when writing the constraints later. And then we have the duration in days. How many working days does it take to do this job? And then we have that tag set, right? That set of tags that if 2 jobs have the same tag, they should not be happening at the same time. How does that go into the database? Well, unlike the normal easy properties, these properties actually need, you need to map this in JPA. You need to tell them, what do I do with this too-many relationship? And this particular way in an element collection is a really easy way to just say, just consider it part of this class, and you store it in a different table, but just eagerly fetch it every time you read one of those jobs. So when you read a job, it actually reads all of the tags for that job too, and make sure those are filled in. Now, you shouldn't overuse eager fetching, because before you know it, you're eager fetching your entire database. But for this particular case, for this particular property, this is 100% fine, so we'll do that. So what else do we have? Well, we need to assign a crew to this particular job. I need to assign a start date and an end date, of course. Start date is again inclusive, end date is again exclusive. The crew, this is a many-to-one relationship, as explained earlier. This, again, we need to tell Hibernate JPA about that this is a many-to-one relationship, so that's where this annotation lies. So then it will actually, in the database, it won't actually put the crew in there, it will put a foreign key of the crew in there, which will be, of course, the ID of that crew. And then we have a whole bunch of constructors, toString methods, getters, and so forth. Now there's one special thing. That's the end date. The end date is actually not really we want it in the object. So when we send it to the UI, the end date is just available there, but you can calculate the end date. It's actually the start date plus the duration in days. So when you set the start date here we have a setup for the start date. What we're going to do is we're just going to fill in the end date automatically. So when the start date is null, the end date will also be null, but when it's not null, when the start date is filled in, we're going to take the start date and we're going to plus the number of the working days, add that to that. But like I said, we don't work during the weekend. So what do we do during the weekend? Well, we do weekend padding. Then this is an algorithm that basically, a small formula that basically figures out how many weekend padding days do we need to add to make that correct. And it does that, right? Okay, so now we have our crew and our job element. We still, our entities, we still need to be able to read and put them in the database and read them from the database. And for that, we have these two objects, the crew repository and the job repository. As you can see, they're very, very simple. So what do they do? What is this? This is using panache, and this is saying, it's very much like Spring Data for people who know that. Let me just show you. If we do Control F12, these are all of the methods that are available on this class, like delete one, find one, list one, persist, update, and so forth. So all kinds of CRUD operations, create, read, update, delete operations for, in this particular case, crews, right? And for the jobs, we also want to be able to read and write jobs and so forth. So we have a job repository too. We could be adding additional query methods on here, but I don't need those, so I won't do that today. Okay, so now I can read and write my jobs and my crews to the database. What else do I need? Well, I need to be able to send all of those jobs and all of those crews to the UI. And that's why we have the maintenance schedule. The maintenance schedule is basically a wrapper or along all of the crews and all of the jobs. And this is what we're going to send to the UI. Again, it has some getters, setters. So actually just some getters and some constructors, but that's basically what it is. But beyond that, it also has the start of the planning window and the end of the planning window. We'll need that later because we need to know, which dates can we actually assign these jobs to. You could in theory figure it out by unionizing all of the ready and due dates. But to make it easy, we just have a specific planning window in here of 5 weeks that will so we know the from and the to date. Okay, now one more thing I want to show you is we have some demo data, right? So if you actually look at this, you can see there's a bunch of demo data here, all of these jobs, all of these crews, right? And that is actually created in the demo data generator class, right? So let me quickly explain what this does. Basically, when the Quarkus application starts up, this class is going to observe the startup event. And that means that this method will be called every time the Quarkus application starts up. And then in a transactional method, what it will do is it will create, in this case, a number of crews, alpha, beta, gamma crew, and it will persist those crews into the crew repository, so we'll persist those in the database. So every time the Quarkus application starts up, we're going to fill the database with a bunch of demo data. Now, you might wonder, doesn't that mean we always keep adding more and more data? No, because if you go in application properties, what I've done is I've said, okay, every time the Quarkus application starts up, I want to drop the entire database and recreate it from scratch, right? And oh, by the way, we're using H2 as a database and it's in memory. So, that's also a way to, you wouldn't be using this in production, of course, right? In production, you would probably use not H2, but PostgreSQL, MariaDB, or whatever other database you prefer. And of course, you would not be dropping all of your data every time you start up. But during development, this is extremely easy when you add extra properties, extra fields to your classes, extra entities, that you don't have to worry about the database schema, right? I don't have any DLL statements anywhere in this code. Okay, so let's take a look. Let's show, and I said earlier that I really like the Quarkus Dev Mode, and I'll show you now why I really, really love that. So what I'm going to do is I'm going to change this test data, and I'm going to have now changed gamma to delta crew. And when I actually go to, oh, that's the wrong way to go to there. When I actually go through the UI, you can see this is gamma crew. I'm going to press the refresh button, and what you will see, it's instantly changed to delta crew. Now, let me tell you what happens here so you really understand the magic behind this, right? So as long when I make the change, nothing happens in the code. But when I, in here, in the browser, click the refresh button, a REST method is going from the browser to the server, right, to the Quarkus server. And Quarkus says, okay, I see a REST method coming in, but I also see that one of the files on disk changed, right, because we were developing, making changes. So what it does is it says, okay, I'm just going to shut everything down. I'm going to completely restart the application. I'm going to run the startup event again, clear the database, drop the database, recreate the schema of the database, put all of the test data in the database, and then I'm going to continue the REST method as nothing really happened, and it'll show you these changes. Now, how long does that take? How long does that entire thing take? Well, it actually shows here at the bottom. Well, this case it actually took more than a second. Usually it doesn't take at all that long. So let me do this. Let me change this again, epsilon. The epsilon crew. Let's go back over here. Let's click the refresh button, right? You can see it changed to epsilon. So the database also changed. And this took, again, 1.1 seconds. Okay, probably because of the screen sharing. Usually it takes 600 milliseconds. But anyway, 1 second, I can live with that. I can live with a round trip of a little over a second. So this is the real power of Quarkus. You make some changes, you immediately see those changes in the UI. Let me show you one more time, right? The Gamma crew, go back to original code, go back to over here, click refresh, and you'll see that it's immediately changed to Gamma crew. And I'm wondering, does it stay that long? Well, it's going down a little bit, but it stays a full second. This isn't, so anyway. Okay. What else do we need? Well, in the application, we want to click the solve button, and then it will actually assign those unassigned jobs here to somewhere to these crews and to those times, right? So let's click that solve button for a second. Error. Like I said, there is no OptaPlanner code in here. There's no AI optimization in here yet. That's the part we actually need to write. So let's see what happens there on the backend. Well, of course, there's a method here, and actually, you can see here, this is the problem. There's a REST method to where I call the solve method on and not unsupported operation exception. So this is the part we'll actually need to write in a few seconds to fix that error and actually get it to do some optimization. Before we do, let me also show you the rest of this REST class. This is the only other class I didn't show yet. This is the resource class, the REST class. So this is listening to the /schedule path. Every time we do a get method on that, it will load the schedule. What is loading the schedule? That means this is a transactional method. And this will actually go in the crew repository, give me all of the crews, sort them by name. The job repository, give me all of the jobs, sort them by due date, then by ready date, and then by name, and then by ID if they're still the same. You can see I've also hard-coded the from and to date of the planning window here for simplicity's sake, but in a real application you wouldn't do that, of course. And then this returns back to here and is returned from the REST method. Now notice something. This is actually calling a transactional method which is a protected method on the same class, right? So you can add, even though it's calling itself, you can add a transactional annotation here, and that actually works. So that's quite nice. That the transactional annotation, even when you do an inner call within the class, still works, and so forth. Anyway, we need to implement the solve method. So how are we going to do that? Well, let's go back to the next part. Let's add some AI optimization to all of this, right? Let's do some live coding. So we're going to add OptaPlanner, right? It's already added in the extensions. So now we're going to add the code for it. So what do we need to do? Well, we need to tell OptaPlanner, what can you change during solving? What can you change during solving? Can it change the name of a job? No. Can it change the ready date of a job? No. It wishes it could, but can't, right? Those are all input. What it can change are these things. It can change the crew and the start date. Those are two orange things, the crew and the start date. Now the end date will change too, but that's actually a side effect of changing the start date, right? That's the end date is the start date plus the duration in days without weekends, right? We already did that to the setter method. So we're going to focus on the crew and the start date. And so the things that change during planning are called planning variables. So we're going to have to tell OptaPlanner, these are things that you can change, right? By adding a planning variable annotation. Now, the class that holds one or more planning variables is called a planning entity class. That's a class where some of the fields change, some of the properties change, and so that we'll need to add a planning entity and a class annotation on the job too. Now, before we give the jobs to OptaPlanner, to the solver, the crew, the start date, and end dates fields will be null, but after solving, they will be filled in, right? And taking into account all of the other jobs and taking into account all of the crews and all of the constraints to figure out something which fits for all of these things, not just for one job, but for all jobs, consistent with all of the other jobs, right? So let's do that. Let's go to the crew class. Let's say, okay, OptaPlanner, this class has things you can change. This is a planning entity class, right? And particularly, you can not the crew class. We don't want to change the crew class. That's like I shown here. It would be stupid. We're not changing anything on the crew class, right? So let me do it right. Let me go to the job class and let's say, okay, job class. We're going to change things here. So we do add planning entity. This is changes during planning. And then it's going to be the crew that changes. So what we can do here is say, okay, planning variable, this changed during planning. We need to somehow tell it, here's the crews you can select from. OptaPlanner doesn't know there's an alpha, beta, and gamma crew, right? It needs to get it from somewhere. So the way you do that is you say, okay, I'm going to give you an ID, which is the crew range. And somewhere else, we're going to give it a list where we have the list of crews. We're going to hook that into this crew range ID, right? That's a value range provider reference, basically. Now, you could do the same for start date, but there's a problem. If you put it on the fields, then OptaPlanner will directly change the start date field without that the end date field is changed. So instead of adding it on the fields, this time I'm going to add it on the getters, right? So for the crew, that doesn't really make a difference. It will go to the get and set crew method. But for the start date, it will make a difference because when I put the planning variable on here, that means that whenever OptaPlanner changes the start date, it goes through this start date method. And as a side effect, it also updates the end date field correctly. So that's exactly the behavior I want. So I'm going to add it on the getters in this particular case. So over here, we're going to say, okay, this is a planning variable, also the start date, and you can select from the start date range, which I'll now actually create for you. So where do we get the list of crews and where do we get the list of start dates? Well, in the maintenance schedule object, this is what we're going to give. This is the object where we're actually going to give to OptaPlanner to solve, which has a list of all the crews and all of the jobs, right? To where it needs to, for each of those jobs, give the crew and a start date. And so after that's solved, OptaPlanner will give that back to us, and that will be a planning solution. So we add a planning solution annotation to say, okay, this is the input and output coming back and forth from OptaPlanner. And like I said earlier, we need to give it this particular list of crews. That's the list we can actually fill in over here, right? That's the list that OptaPlanner can use to call the set crew. So any of those in that list can be called for each of the job instances here. So what I need to do is somehow tell OptaPlanner this is where you can pick from, right? So this is a value range provider, and the ID is that crew range, right? So that particular ID, crew range, is actually the same as this one over here. And now OptaPlanner knows I can pick from those. We also need a list of all of the start dates. Now, you might not see those here out of the box, but what we can do is we can say, okay, let me just add it here with the method. We're going to create a method that gives me a list of all of the start dates. So which are of type local date, create start date range, right? And this is the value, this is a value range for that start date range, right? How do we get that? Well, we just say, okay, give me the from date. This is the start of the planning window. Give me all of the dates until the to date, right? Then we could say we give that into a list. The problem with this is this will also select weekend days. This will give me all of the planning, all of the start dates between the from and the to date, but including weekend days. So weekend days is bad. What we're going to do is we're going to filter those out. We're going to say, okay, if a date get day of week is actually, it must be different than Saturday, because if it's different than if it's the same as Saturday, then we don't want to return it. And also, it must be different than Sunday, of course. So day of week must also be different than Sunday. Okay, here we go. So now OptaPlanner has all of the start dates and all of the crew ranges. When OptaPlanner finds a solution for this problem, it will also a state of jobs being assigned to these crews and these start dates. It will also yield a score saying how many hard constraints and how many soft constraints are broken and that kind of things. So we need let's add a field to actually capture that, the score field. And we need to add a planning score annotation on that. So this is basically when OptaPlanner starts assigning these jobs to these crews, then it will actually fill in the score field for us. And let's create a getter for that score field. So here we go, a getter for the score field. This is of type hard and soft constraint. That means that some of the constraints need to be fulfilled. Those are hard constraints, and some of the constraints should be fulfilled, and those are soft constraints. There's one thing that's OptaPlanner that's missing, and that's what is the list of jobs. So we're going to tell them, okay, here's our list of jobs. This is our list of planning entity collection, right? This is how OptaPlanner knows, okay, here's where I can get all of my jobs. And then in the job, it will see, okay, in those jobs, I can change, let's say, the crew variable and the start date variable. Okay, our schedule is ready. Let's hook this in, right? So what we're going to do here is we're going to add a solver manager. This is the thing that will solve the problem for us. And it's going to be for that maintenance schedule. That's our input and output thing. And we're also going to have to give it a type of ID. This can be anything, a string, a long, or anything, if we would give it multiple things to solve. But today we're only going to give it one thing to solve, right? We're going to inject this using dependency injection, just like we get the crew repository and job repository, we get the solver manager. So the solver manager is created by Quarkus automatically, and then in Spring this is very similar, of course, right? Based upon the annotations on the job and schedule and so forth, it creates a solver manager that can solve our problem. So now what we can do is we can say, okay, solver manager. When we get the solve call, when we get this unsupported operation exception, what we can do is we can say, okay, solver manager, I need you to solve my problem. So we're going to call solve and listen. Why listen? Listen means that if we see updates, improvements to the solution, we're going to immediately show those in the UI, even though we continue solving to find even better solutions. That's why we do not just solve, but solve and listen. This is not a badge job. This is we immediately want to see the results of that. Any such job first needs to get a problem ID. That's because we only have one, we're not going to solve multiple data sets or multiple problems, multiple schedules. I'm just going to hard code that to one. And then it needs two methods, one to read the problem and one to write the problem. So the first method, given that problem ID, which will be 1L, when it's ready to actually start solving, we're going to just load the schedule, which is this load method, which I talked about earlier, right? Which just gets all of the jobs and all of the crews from the database. And then when we actually need to save the schedule, so when we have a schedule, a solution, and we need to save it, we're going to call the save method, and we're going to give that the schedule. I've not talked about the save method before, but what it basically does is it stores the crews and the start dates in the database. It takes the in-memory jobs and actually figures out, okay, what's the job in the database, and it adjusts those to the attached job. If you're familiar with JPA, basically the job that's mimicked in the database, and it will set the crew to the same job and the start date to the same job, right? So now when we click the solve button, we're going to solve, it's going to load the database and save. There's one little thing missing, and that's constraints. We have hard and soft constraints, like we should not be planning a job before the early date. Where are those? So let's add one. Well, those are in the constraint provider, right? So let's add a constraint provider. So what I'm going to do is I'm going to create a solver package. I'm going to create a Java class called maintenance scaling constraint provider. I'm going to implement the constraint provider class, constraint provider class. I'm going to, that has one method, the define constraints, where we define all of our constraints, right? And in this particular one method, right now, I'm just going to return an empty error. array. So I'm going to say, okay, there are no constraints. Do whatever you want, OptaPlanner. Let's see how that works out. So we go back to our UI. We click refresh, right? No errors, that's good, everything worked. And when we click the solve button, OptaPlanner will assign all of these jobs to these crews. What it actually did is it said, okay, there are no constraints, so I'm going to assign everything to the alpha crew, and I'm going to assign everything to day one of the alpha crew, right? And the UI doesn't really cope with this quite well, but it actually put all of the jobs on the same, on the first crew. And if you see them by job, you can see this too, right? Every job is assigned to the 1st of November, and they're all assigned to the alpha crew. This has a couple of problems. So first of all, there's a hard constraint, if you remember, that says every crew can only do one job at a particular time, right? And so clearly we need to add that. So let's go back into the code here and let's actually add that. So when we have two crews that, when we have two jobs that have the same crew at the same time, we have what they call a crew conflict. So what I'm going to do right now is I'm going to create a constraint. See a constraint. This method will create that constraint that says don't do that. There are different ways of doing that. You can write a for loop and so forth, but the most scalable, the most efficient way is using our constraints API. We have simpler APIs too, but this one is it's actually not that hard, but it is the most efficient. It does delta calculations underneath. It uses hash tables underneath. It's very, very scalable, right? And so what we're going to do is we're going to say, okay, I'm going to select all of the jobs. So this is like an SQL query. I'm going to say from all of the jobs, right? So job.class. Here we go. Let's import that class. Here we go. And then I'm going to say join, like in SQL, join me with any other job. And if you have two jobs that do certain things, we're going to penalize that as a crew conflict. And more particularly, we don't want this should never happen. There is no reason this should ever happen. So we're going to make it a hard constraint. Now, this will just select the job and any other job and will penalize that. That's not what we want. We want to penalize the jobs that are happening for the same crew on the same day. So what we want to do is we want to say, okay, the second job, given the first job, this one needs to be equal for the crew. So the job get crew needs to be the same, right? So if now we have those two jobs, only the two jobs which have the same crew are being penalized. But that's okay if they're not overlapping those two jobs based upon their start dates, right? So what we need to do is we need to also check if they overlap based upon their start and ending dates. So luckily we have a function for that in OptaPlanner called overlapping. So then when we say, okay, given a job's start date and given a job's end date, it will figure out, okay, when these two jobs actually overlap, when the first one starts before the second one ends, or vice versa. It's actually not that easy overlapping as you might think. Then we have two jobs at the same time for the same crew, so at least 1 day or more days, right? So how does that look when we actually go into when we actually restart the application, right? So I've just added that one constraint. Let's see how this AI in action. This looks better, right? There's no crew that has two jobs at the same time, right? Alpha crew can first do Uptown Avenue, then Downtown Bridge, Uptown Street, and so forth. It never has to do two jobs at the same time. There are still some issues. You can actually see them in red here, right? Some of these jobs are too early. Actually, let's take a look at the other screen. This is actually more clear here. Like, for example, this Alpha crew job, the Uptown Avenue one, starts on the 1st of November, but the ready date is 4th of November. So clearly we're missing a few hard constraints, right? So let's add those two. Let's go back to our constraints. And let's say, okay, I want that ready date thing, right? Ready date. I want to actually take that into account too. So I'm going to add a constraint for that. Here we go. Create a new method. And so how do we write a constraint for that? Well, we don't need to find two jobs that somehow conflict. We just need to look at every job individually and say, okay, when we have a job, so let's select a job. Here we go, from a job, right? And then we're going to filter them on where the start date is before the ready date. So when we have a particular job and the job get start date is before the job get end date. And oh, by the way, this is of course using local dates, so Java time from Java 8. And so all of these nice methods are in there. Always use Java 8 times, never use Java-util date for these kinds of things, or you'll go crazy. But anyway, if you have a job that the start date is before, not the end date, but before the ready date, of course, right? Then we're going to penalize that. We don't want that. We're going to hit OptaPlanner on the head. Stop doing that, OptaPlanner. And we're going to say, okay, this is again a hard constraint, right? So we're going to say hard soft score 1 hard. Here we go. Let's see what happens. We go back to the UI. We click the refresh button. Here we go. We click the solve button. Here we go. And let's take a look at the jobs. And what you see is that right now all of the jobs are nicely, no job is starting too early, right? We still have some jobs that are overdue, that start too late. Let's fix that too. That's actually quite simple. We take the same code. I'm going to just speed it up a bit here. So what I'm going to do is say, okay, I'm going to add a due date constraint, right? And so here we say a due date constraint, and say when we select a job where we have a job where the end date is after the due date, right? When it ends too late, right? Then we're going to penalize this as a due date, again with 1 heart. And again, if we go back to our UI, you'll see that now if we solve this, here we go, you see that you still have a couple of jobs too early. Let's take a look. What's going on? Did I make a mistake, or is it still solving? Good.
Maybe you forget to add the ready date constraint.
Yes, good one. Thank you. Thanks, Sergey. I somehow deleted it when I added the due date one. So here we go. Live coding is always fun like this, right? This time I actually didn't get an error, so that's always good, right? Usually I get an error because I miss an annotation somewhere. I then add it and then we continue. But anyway, let's see. Okay, let's solve this. Here we go. And look, every job starts within the time window, starting at the ready date, in this case, or after the ready date, ending before the due date. So that's perfect. Look, all the jobs are good. If you look at them by crew, we can see every crew can do their jobs. You can still see there's things like these downtime, right? You can see that these mutually exclusive tags are still in there. Due to lack of time, I won't go into those today, but given with a few more minutes, we can actually add that constraint easily too and say, okay, when we have 2 jobs that have the same tag, like downtown here or subway, and they're happening at the same time, let's penalize that. And so OptaPlanner stops doing that too. And that's typically what you would do as a soft constraint. So just for information, so there's 2 types of constraints, hard and soft constraints. Hard constraints must not be broken. Soft constraints should be avoided, right? Right now, I've just shown you how to add hard constraints, but switching to soft constraints is quite easy. You can just say, okay, this one is a soft constraint, and then breaking any of these soft constraints will be less important than not breaking any of these hard constraints, right? That's how you could change that. Okay. If you want to get started with OptaPlanner and Quarkus, the best way to do that is you just say, okay, I git clone the OptaPlanner quick starts. One of the quick starts is actually this maintenance scheduling example, which I've just shown you today, with a little bit more bells and whistles and a little bit more constraints, including that mutually exclusive tags and so forth. And so you just git clone it. You go into one of the use cases directly, just as maintenance scheduling. But again, we have vehicle routing in there. We have facility location problem. Conference scheduling is not in the quick starts; it's in the examples, but we'll soon come to quick starts too. Lesson scheduling, we all have those. And then you just do Maven Quarkus Dev. You go to localhost 8080, like I've shown here, and you can actually run those applications on your own machine. And you can start fiddling with them and adding some constraints or removing some. Now, if you want more information on OptaPlanner or Quarkus, These are the websites. If you have feedback about this presentation, I'll gladly hear it. But let's go through the Q&A right now.
It looks like we have no questions in chat. So guys, feel free to ask whatever you want, and just maybe to share some impression. It looks like I have been working long years ago for Intel compiler team, and with task you just shows quite similar to instruction planning when you plan your assembly code. It's
Yes,
quite
absolutely.
funny.
Yeah, it's amazing how full the world is of planning problems, right? Just if you take an airplane, the security guards at the entrance of the at the gates to go through security, that's a shift planning problem. Which security guards gets which shift at which time and stands where. You have all kinds of interesting constraints there, like you need a male and a female at every position potentially for swap downs and so forth. You go to the gates, determining which airplane goes to which gate, planning problem. Which physical airplane takes you to which location, because if airline has multiple airplanes, planning problem. Maintenance on those airplanes, and again a planning problem. You take a train. Trains are the Valhalla of planning problems. They're which train takes you where, which driver drives which train, what time does which train arrive, and in which order do they go to the stations.
Actually,
All of those can be optimized.
Actually, I could add some examples from finance, but okay, let's skip it. And I think it's time to stop our presentation and move to discussion zone. So Geoffrey, thank you for your talk. It was quite interesting and very, very useful. How could it just simply be done here? So I think everybody, guys, we're waiting you at discussion zone. So I think we share a Zoom link quite soon. So Geoffrey, thank you.
You're welcome. Thank you.